Hi class, let's do some more linear algebra. As usual, A is going to be an n by n matrix. What we've been talking about so far, in particular in the last lesson, is the relationship between the determinant of A and singularity. We know now that the determinant of A is 0 if and only if A is singular. Let's write this another way. Equivalently, the determinant of A is not 0 if and only if A is non-singular, i.e., the inverse exists. This lesson is going to focus on inverses of matrices. So let's just make sure that we're all on the same page and recall that the definition of an inverse goes like so. A is an n by n matrix. A inverse is the n by n matrix such that A times A inverse is equal to I is equal to A inverse times A. Let's explore this a little bit through some exercises. Here's an exercise for you. Assuming that A is non-singular, as in A inverse exists, show that A inverse is unique. A single matrix does not have more than one inverse. Here's another exercise for you. Assume that A times B is equal to the identity matrix for some n by n matrix B. Show two things: that A is non-singular and that B is the inverse of A. This one is a little bit tricky, so here are some ideas to play around with. Of course, there's always multiple ways to prove anything, but here's some things you might want to think about. So some ideas. Well, if A times B is equal to I, then there's a way to think about the fact that A times B as a matrix is non-singular. Why? Think about it. If A times B is non-singular, there's a way to move from that idea to the idea that B itself is non-singular. If B is non-singular, we can move from that to show that A is B inverse, and from there to show that A itself is non-singular. These steps require some work, but you do have everything that you need from previous lessons. Question. Okay, we've been exploring the determinant, and the determinant tells us when A inverse exists, but how do we actually find it? Well, to find A inverse, we're going to explore two methods. A, the partitioned matrix method, and B, using something called the adjoint. Let's do this one at a time. A, the partitioned matrix method. Well, step one, confirm that A inverse exists. This might be given to you, or you could use the determinant or some other method. Step two, set up a partitioned matrix that looks like so. A on one side, the identity matrix on the other side. Step 3, perform elementary row operations to get a different partition matrix, I on one side and some other matrix, B, on the other side. Then we will claim that B is equal to A inverse. Note here that this is possible because if A inverse exists, as in A is non-singular, this implies that A is row equivalent to I. See Theorem 5 or the updated Theorem 5, Theorem 19. Let's use this method to do an example. Example, A is 2, 5, 1, 3. Find A inverse. Well, we're assuming that A inverse exists. Set up your partition matrix with the identity matrix of the correct side on the right-hand side. Now we're going to be doing a series of elementary row operations in order to reduce to the form that we want, where the identity matrix is on the left-hand side of the partition. First things I'm going to do is exchange row 1 and row 2. I'm going to get 1, 3, 0, 1 and 2, 5, 1, 0. Then I'm going to create a new row 2 by taking the existing row 2 and minusing 2 times row 1. This doesn't change row 1, but row 2, we're going to minus 2 times the original row 1 and get 0, -1, 1, -2. Then I'm going to create a new row 1 by taking the old row 1 and adding 3 times row 2. This doesn't affect row 2, but it does change row 1. I'm going to get 1, 0, 3, -5. Last step, I'm going to scale row 2 by -1 to get 1, 0, 0, 1, 3, -5, -1, 2. Via this method, A inverse should be 3, -5, -1, 2. Quick multiplication will show that this is actually the inverse that we were looking for. All right, I just introduced a method for finding A inverse. Sure, it works, but why does it work? Well, let's walk through the theory of this method. If A is non-singular, we know it is row equivalent to the appropriately sized identity matrix. And what does that mean? i.e., there exists elementary matrices E1 through En such that, well, I is going to be equal to E1 through En applied to A. Left multiplication by an elementary matrix does the same thing as an elementary row operation. So a series of elementary row operations can just be represented by left multiplication by some elementary matrices. Taking this, I'm going to multiply on the on the right-hand side by A inverse. We're assuming that A is non-singular, so A inverse exists. What I get is that A inverse is equal to E1 through En times I, since matrix multiplication is associative. All right, take a step back and think about what the takeaway here is. Consider the row operations needed to transform A into I. These same row operations represented by the matrices E1 through En, these same row operations will transform I into A inverse. Let's talk about a quirk of this. So if I is equal to E1 through En times A, then A inverse is equal to E1 through En times I, which is E1 through En times E1 through En times A. Apply those elementary matrices twice to A, you're going to get the inverse. Here's an exercise for you. Exercise. Use the partitioned matrix method to find A inverse when A is equal to 1, 2, 3, 4. Let's learn a different method, the adjoint method. Adjoint. I've heard multiple pronunciations. Definition. If A is equal to Aij, is an n by n matrix as usual. And just as a reminder, big A sub ij is the cofactor of little aij, the entry. Then the adjoint of A, well, it's a matrix. Here's the notation. And here's what it actually is. It's going to be A11 through AN1, A12 through AN2, A1N through ANN. On the surface, this might look like just replace every element in A by its corresponding cofactor, but that's not exactly true. It's the transpose of that. Because notice, this is the row, and this is the column of the element that it corresponds to, but it's in the n, first, m, 1th position. Okay, so that's a little quirk of this. All right, we've defined the adjoint. How does that tell us what the inverse is? Here it is. A inverse is 1 over the determinant of A times the adjoint of A. Let's do a few examples. Example. This is kind of a generalized example to refamiliarize ourselves with something that we kind of already know. Say A is a generic 2 by 2 matrix, A, B, C, D, such that, well, A is non-singular. We want to make sure that an inverse exists. Then, the determinant of A, as we know, is AD minus BC. The adjoint of A is going to be A11, A21, A12, A22. let's work out what this is. So if we've got A, B, C, D, well, and I want to find out what A11 is and what A12 is. And I want to find out what A21 is and A22 is. Well, A11 is the cofactor corresponding to little a11 in the 1, 1 position. We're going to ignore the column and the row that it's in, and we're going to get -1 to the 1 plus 1 times D, and this is D. If I want to find out A12, that is the cofactor, well, plus corresponding to this B here, which is in the 1, 2 position. We ignore the row and the column that it's in, and we get -1 to the 1 plus 2 times the matrix that's left, C. This is -C. Let's draw another matrix just to stay neat. A, B, C, D, that's our matrix A. If I want to figure out what big A21 is, I'm going to be looking at this entry here in the 2, 1 position. Ignore the row and column that it's in. This is going to be equal to -1 times to the 2 plus 1 power times the matrix that's left, that is B. This is -B. And last but not least, if I want to find A22, that corresponds to this guy right here, ignore the row and column that it's in, I'm going to get -1 to the 2 plus 2 times A, which is A. Putting this all together, the adjoint of A is going to be D, -C, -B, A. And by the formula before, A inverse is going to be 1 over the determinant of A times the adjoint, D, A, -B, -C. This is the formula that you know, of course, and this is where it comes from. This is very general. Let's just do an example with our matrix 2, 5, 1, 3. We know that the determinant of A is going to be 2 times 3 minus 1 by 5, which is 6 minus 5, which is 1. A inverse via this formula is going to be 1 over the determinant of A times the adjoint. Negate B and C, reverse A, exchange A and D, and this is 3, -5, -1, 2, which is of course the answer that we got before. This seems even weirder than the method that we had before, so let's talk a little bit about why this actually works. Well, to do this, we're going to have to recall lemma 16. AI1, AJ1 plus ... AIN, AJN. This is going to be the determinant of A when I is equal to J and 0 otherwise. So let's talk about what A times the adjoint of A is. This is just simply the multiplication of two matrices. Let's call these entries Cij. Let's work through the idea of what this product is going to be. Here's the idea. All right, I'm going to do this for a 3 by 3 matrix so that we can actually see what's going on. So I'm going to have A11, A12, A13, A21, A22, A23, and the third row. This guy's A. We're going to multiply it by the 3 by 3 adjoint. This is A11, A12, A13, A21, A22, A23, and the third column, A31, A32, A33. This guy is the adjoint of A. And let's talk a little bit about the entries of this product. Let's look at C11 for a second, which is going to be right up there. C11, by the definition of matrix multiplication, is going to be the dot product of the first row in A with the first column in the adjoint. Okay, so this is going to be A11 times big A11 plus A12 times big A12 plus A13 times big A13. This is the determinant of A by the cofactor expansion, or by lemma 16 if you like. The reason that this works is that I is equal to J. I is 1, and J is 1. Let's look instead at C23, second row, third column, it would be there. C23 is going to be, by the definition of multiplication, the dot product of the second row of A and the third column of the adjoint. So this is going to be A21, A31 plus A22, A32 plus A23 times A33, which is 0 by lemma 16. Why does this work? Well, I is 2 and J is 3. I is not equal to J. Okay, so we went through this. What does this actually tell us? Well, A times the adjoint of A is going to be the determinant wherever I is equal to J and 0 elsewhere. Altogether, A times the adjoint of A is going to be the determinant of A where I is equal to J, as in the 1, 1, 2, 2, and 3, 3 position, and 0 elsewhere. And notice that this is the determinant of a scalar times I. Okay, in general, using this argument, if A is non-singular, of course, equivalently, the determinant is not equal to 0, A times the adjoint of A is going to be the determinant of A, the scalar, times I. So here's what I'm going to do. I'm going to multiply on both sides by A inverse, which we assume exists. And what I'm going to get is that the adjoint of A is equal to, well, this being a scalar means that we can bring it out front. We're going to get the determinant of A times A inverse. Since the determinant of A is non-zero, we can divide, and we're going to get 1 over the determinant of A times the adjoint of A is equal to A inverse. There's our formula. This is interesting for a number of reasons. Number one, it's super useful, but you can also get the idea of why singular matrices are called singular matrices. Just an idea. Singular matrices are called singular because this formulation will require division by 0 in the singular case, because the determinant of A is going to be 0. All right. Here's an exercise for you. Find the adjoint of this matrix 3, 1, 2, 3, 2, 2, 1, 3, 3. That brings us to the end, but I'm sure you have a lot of lingering questions. Here are some that you might have. This lesson was concerned with finding inverses of matrices. We know that matrices don't always have inverses, but do most matrices have inverses? If you meet a matrix on the street, is it likely to have an inverse? And what does this mean precisely? What does the most mean precisely? Number 2 is that today we found inverses of matrices, but before we were concerned with determinants of matrices, is there a relationship between the determinant of a matrix and the determinant of its inverse? And a little quirk of today's lesson is that we ended up expressing a non-singular matrix as a product of elementary matrices. Can we always do this? Then can you always express a non-singular matrix as a product of elementary matrices? Think on these things. See you next time.